Hello and welcome. I'm Bill Wake. We're working on a program to compare tunes for similarity, and now we're going to do this thing where we try and cluster them so they physically are close when they're very similar. And part of doing that is we have to have some sort of measurement that says how similar are things. So we started down that path yesterday and we'll continue there today. After that, I'm not quite sure. We may be doing more of a research session, trying to figure out what's a good model for the problem we have. All right, so here I've loaded up our no scaling file, which is 39 different versions of Deck the Halls. Okay, and you can see that they have different shapes. So Parsons code gives you sort of I think of it as the derivative of the shape or some sort of, I don't know, it's something like that. It doesn't care how far you're jumping, it just cares which way are you jumping. So this one is mostly going down, this one goes down a little, and then up. And then we get some others, like this 34 and 32 aren't the same, but they're pretty similar. 22 is very similar as far as it goes. And let's see what else. Well, that's sort of like the others. These two look identical or almost. But yeah, these have some similarity, but I can see that this one is not the same as this one. This one's very down oriented. This one's very horizontal. This one's very up, and this one kind of bounces around forever. But we want to say what's close and what's far away. And if we drew this on a 2D picture, maybe just enough room for the names or the numbers or something, I'd like this one, 32, to be very close to 34, and 22 to be pretty close to 34 as well. But 35, nah, not very similar. I don't think it belongs together. It should be over on the side somewhere or something like that. So our job today is we're going to define a similarity function, and it works by, in effect, overlaying, putting the stars over. Imagine them on, cellophane, clear cellophane, and overlapping with the stars located at the start of the same point. And then we're going to draw some sort of shape that captures the shade between them is sort of the area difference between them. Okay, so these two, 33, 31, it looks like if you laid them over, they'd be pretty close to no differences up to here. And then this one has a little bit of a tail that's different. Now, whereas if you took this one, 7, it goes down further, it goes up differently, it goes down further, it goes up. It's going to have some difference. All right, and so we started doing this, and here we just have a test case with a string, C, C, D, E, D, A, B, just a string of notes, and 2 Parsons codes basically for the same set of notes. So they're perfectly identical, and their similarity, I'm treating it for now as a number 0 to 1, 1 being you're just the same thing, okay? Now, we started down this path to say, okay, what if you're different? So if I consider CCC, it's sort of a straight line, and CDE is going up, okay? And so the idea is from C to D, you should say, oh, that's one triangle's difference, and then D to E is another difference, okay? So I'm going to say it's a difference, well, I'm going to say the similarity is a half, okay? That's my theory anyway, because you got 2 notes going up versus 2 the same. That's sort of a difference of a half. They could have been going the opposite way, which is this test, CDE versus CBA. So up versus down. That gives you kind of the maximum difference. Up versus down is sort of 2 apart, and these are only 1 apart. So the maximum you can be is 2 apart. And so I treated this as saying this is the maximum distance is 4, and this one, the maximum distance is 2 because it's up versus repeat. Okay. And I think, well, what we're getting is 2/3. Okay. And I think, well, since we only have 3 notes, that tells me like something's going on probably at the beginning. And I guess I'll admit I peeked enough to know. All right. It's this number of notes thing. So the deal is the star versus star, it doesn't really give you any information. And so it really shouldn't be part of the count. There's only 2 changes that we can measure. So I think this should be number of notes minus 1. Okay, because it should only be wearing, this is a no information kind of thing. All right, so let's see if that captures this understanding. Apparently not quite. Okay, cluster tests. Point 5. So the gap is 0, 2, 2. Up versus down is worth 2. So the gap is 4. Let's see what that means. Okay. The number of notes, well, it's really minus 1. So we'll count 3 because we got star, note, note, minus 1. Okay, so it's 2. 2 times 2 is 4. Double of gap is 4 over 4 is 1. Okay, that's interesting. I mean, I'm trying to make it so that, I mean, that's the maximally divergent for 3 notes. And this is sort of halfway, and this is maximally convergent for 7 notes, whatever that is. All right. We got a 0.5. So that should be no difference. This is an up. We're really counting the spaces between them. That's why it's kind of confusing. C to D is an well, C to D is an up, and C to B to A is a down and a down, and they both start with a star. Okay, so what's going on? All right, let's tackle. Yeah, let's see what we got. Okay, so step over this. I don't know if we can print pairs. It's sort of a not real thing until it has to be. Okay, star UU. Oh, star UD. I've got something going wrong there. CBA. Well, the fact is, I don't know these. This is ABC parser. We'll have to look. Let's find that standard. And get notes. Note. No pitch. Okay. C. A, B, C. Oh, no. Excuse me. So A and B, letter capital C is down here, A and B. So it was C, D, E. This should be up, down, right. Okay, so B, A. All right. We really wanted this comma version, or maybe start somewhere different. Let's make it FGA, FED. Okay. FED is lower, FGA is higher. Okay, so I guess we'll just continue and run that again. Okay. All right, so we've made similarity work for same up versus repeat and up versus down with notes with tunes of same length. Now, the formula we have, let's go back to running. So the formula we have now, it's very forgiving of this kind of difference. So these two start, I mean, they look like they're essentially, oh no, this one's got 3 little peaks here and this one has 2, but they're very close, okay? And if we diffed them, if we computed their similarity right now, we take the shorter length and then compare all the notes that are in that list. All right. Now, should that be a 1, saying it's a perfect match? I don't really think so. I would almost say like this one, I mean, it's not a good a match up to here, but it's a more close match the back third or so. Maybe we can find that one looks really good. This one's pretty good. Okay. I think the ones that are the same length should get some credit. Otherwise, you just have, you could just have 2 notes that happen to be lined up the same direction as this and get 100%. That doesn't sound fair, or at least helpful. I guess fairness doesn't come into it. All right. So I want to scale it differently. Let's turn that into a test. Okay. So function test similarity of tune versus fragment is scaled by matching length is what I think I want to do. So if you have, well, let's do the test case. FGA BCD, and this one is FGA. Okay, I don't think they should be a 0 difference. I'm sorry, it shouldn't. Well, I believe this will pass, and I'm arguing I don't want that. Right. I would say instead, well, there's 1, 2, 3, 4, 5 versus 1, 2. I would say that should get, well, actually, I want to make my fractions work out. So 2 versus 1, 2, 3, 4, 5, 6. 7 letters, so 6 gaps versus 2 gaps. So this, well, let's make it, okay, 1, 2, 3, 4, 8, 9. So there's 8 gaps, differences, and 2. So I would say this should really be 0.25. Okay, that it only gets credit. Basically, we're scaling it by the percentage of common characters, not counting the star. Okay, so the first one has 9 characters or 8 gaps. The second one has 3 characters or 2 gaps. Even though they're a perfect match, they this one should lose some points because it doesn't have as many chances to go wrong. Okay, and we're getting 1, of course. Okay. Now, so I believe what I want to do then, let's see, I think we've moved beyond this. All right, we've paired them together. Okay. We'll take that to be the score, and then we're going to return something. Well, let the what's this? It's the length ratio. Now maybe I should just multiply by the length ratio. I want to say that is description dot count. Maybe I can just give off the links, and then well, let's make this 1.0 for a moment, and return score times length ratio. Okay, but I think I would be content. Well, is that right? Let's make this one 12, 3, 6, 9, 12. Okay, so I'm going to go by the lengths of these things and say your length gives you the scale of chance. Okay, so this one is 1/4 as long, even though it's got a perfect match, it's only 1/4. All right. And so this is description dot count. Well, let's try, let count 1 equal description dot count. Let count 2 equal other dot description dot count. And then let length ratio equal, let's take the min of count 1, count 2 divided by the max. Oops, I better make these doubles before I divide them. Okay. All right. So I think that is good. Hello, meow meow. Welcome back, I guess. All right. Okay. So I think we have reasonable answers for our cluster similarity. So if they're perfectly matched, they get a 1. If they diverge a little bit, kind of by 1 point each time, they're going to be more like a half. And if they just completely divergent, they get a 0. And then if you're shorter, then you multiply your answer by the length ratio. Okay, and then I think we could also say, let's verify the flip. This should be symmetric. So Parsons 2 similarity with 1 should be the same thing. I don't want anything to blow up because it's in a backwards order. Okay, so we make similarity score is scaled by the ratio of lengths of the descriptions. Okay. Now, I'm kind of assembling pieces, and that may be a mistake. I don't know. but I don't know what I'm doing. I mean, I'll put it that way. I've got I've got some ideas. I have some old background in it, but not too current. And I don't know, I'm not quite sure how we want to go about it. But this thing is a transform. We're going to call it clustering. So far, we've left everything on Parsons code. No, I really do care about 0.25. I want it to be, I want it to be scaled by length. So if this is a 1 and it's a quarter the length, I really do want it to be a quarter because if I go back to my run, and welcome voice of unreason. See, it's your first time here. Okay, so I'll take the standard file we've been using, deck the halls, and as I imagine fitting these, this one fits pretty good, but it's only 2/3 as long, so it should not, even if it's a perfect fit, which it isn't quite, it shouldn't get a full credit as compared to one that's 100% the same and the same length and everything. And I really do want, I want them to come out more different. If they're going down, 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 and this one's going up, 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 I want that to really be reflected in the scale difference. I would say, I mean, I definitely don't feel like I'm overfitting. I almost feel like, if anything, my critique would be, am I not doing enough variety? And partly I'm being lazy because I'm picking, powers of 1/2 that I know will divide out. But I do want them to be reflective of some difference. So I think the more refined that is, the better my my answers are going to be when I start trying to place them. Okay, if they all look like they're either 0, 1/2, or 1, you can't really do much with that. So I think more spread is going to be better, and I do think there's enough difference in these that it should be showing up. Now we're anchoring both to the front, and that's got some limitations, but I'm not quite willing to go. I mean, you could make an argument, like, I think this one looks like it's, I can't tell if it is. Let's say they were shifted by a beat or two. It might be better if you, like, maybe this one has a couple notes intro, but if you took off those notes, they would line up perfectly. And, so the way we are now, we're tying the star together, but you could imagine, overlaying them and then sliding them around until you found the best fit. And so, like, this piece here in 29 might really be a really good fit for this piece out of the middle of number 1. And I won't see it because the part I'm, maybe this is only some, I don't know, it's a fragment of the middle and it just doesn't correspond to the front. So I'm still limiting it somewhat. And I don't know a better way to do this sliding thing is like try each position of overlap. Maybe, maybe it's only the notes that are there, but it's somewhat bounded, but still it's going to be a comparison, a different starting point for everywhere from here to about here on comparing these two. So I think more refinement will help us spread things out better on a 2D graph. So the place I'm looking at now is, what I think I can get is I could take all these similarity scores and I could compare n by n, or half of them. They're symmetric, so the triangle kind of matrix. But I could make a matrix that has 34, 22, 28, 29 on the left, and then 34, 22, 28, 29 going across, etc., and fill in each pair by pair. What's your comparison score? So 34 versus 22, 28, 29, 32, and so on. Then 22 versus 34, 28, 29, and so on. Build up that whole matrix and say, as if I'd said, here are the distances between all pairs of points. I want you to reconstruct the 2D image, place those points in such a way that those match up. Okay. And so we could go on and create that 2D matrix of score versus score. But I think I'm going to move into the research portion of today's show. I don't know the right answer for how to best compare these graphs. So let's see. Define a similarity measure. Okay, we've defined it. It's maybe not perfect, but it's defined. So let's track that as done. April 4th. Wow. Okay. But I also did a little research, and I can share these. Let's see. Oh, here. Nope. I must have a window for it. No. Okay. I guess I cleaned up too much. All right. So I started searching for things that might sound like they would do what I want. So what I want to do is, given that 2D graph of every point versus every point, or every song versus every song, I'd like to draw it on a plane, on a piece of paper, such that those distances are respected. So ones that are close together with a distance of 0, they're practically on top of each other. Maybe they are literally on top of each other, but we might want to spread it out a little bit. Given ones that the distance is 1, they should be all the way on opposite sides of the screen. Okay. Sorry. I wrote it as probability 1. So probability of being alike is 1. It's not really the probability, but we'll let that go. 0 is totally different. I'd probably take 1 minus that to get maybe 100 times 1 minus that would give me a number 0 to 100 of how similar they are, percent match or something like that. But I want to get them so that there's clusters, visible clusters. When things said, they were almost identical, they should be clustered, and ones that aren't identical should be out on the edges. And if it's not a match for anybody, it's completely disconnected from any other cluster. But if I go back here, I definitely see a cluster around this kind of shape. This looks like a subset. Those are subsets. This shape is more horizontal, and like this one is. This one's a down. This one's more close to that, but not identical. This one's more down, more horizontal. I'm seeing at least 3 kind of clusters, maybe 4. And I suspect there's probably, 6 or 7 that make sense. And so I want those clusters to appear, and I'm going to put little dots corresponding to each one, and then let you select visually. Yeah. Well, the Parsons code actually handles that. So this Parsons code is saying, here's your first note, your second note goes up, your third note goes up, then it goes down, 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 down. Okay. And this is from the song Deck the Halls, or the root, No Scalon is the root song of that. So dun, 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 it's going kind of down the scale. And that shows up in some of these. Maybe this one very much going down the scale. But because they only tell you direction, up or down, it doesn't matter if they start on the same note or not. It doesn't matter if they jump a little more. They're both going up. It counts as the same, So it's giving you an approximation of the melody shape, but it ignores absolute distances. And so there's no worrying about scaling or shifting per se. It's more if one goes up and one goes down, then they'll definitely start diverging. But even in these two that look identical, they could be totally different tunes if they, the ups are going way up in this one and downs are going way down in this one, and this one's just going a little bit up, a note or up or two, or note or two up or down. Different tunes, but the same Parsons code shape. Okay. And I think maybe before you got here, I was talking about if I needed to compare them kind of horizontally, if they're shifted left or right, you could make a case for that, I think. Let's get back to a case for that. Yeah. So this stretch in 28 to me looks a lot like this stretch kind of going up the big mountain on the middle of this one, and if I score them based on starting at the same place, they look pretty different. But if I said, slide along here and figure out what's your best fit, and it turned out it was here, it'd be a perfect match in here, even though it's too short to match the whole song. That's a future version. I want to get some semblance of clustering out here first, and then refine it. Okay, but yeah, good questions. Okay. So, well, so I'm looking for things that I give you a list of distances and you try and place them on the graph, but they didn't come from making a picture on the page and then measuring their distances. They came more from the distances don't have to match to, it's a multi-dimensional thing. Maybe that's the way to say it. I'm producing sort of a multiple dimension thing of every comparison versus every comparison. And then I'm going to take a view that comes down onto the page, from a particular angle. I look at that multi-dimensional blob and then project it onto the page, and it's not perfect, but it reflects those distance weightings in some way. And I don't know how to describe that. What I looked for a lot was, I think I said given distances between points. Yeah, there we go. Well, points arrange on a plane. Okay, that's one thing I tried. And unfortunately, everybody wants to go the other way for you. Okay. I'd also tried 2D surface. Okay. And others. But this is one of the links I thought was good. Good programs for drawing weighted directed graphs. So here's a nice example. A weighted graph, these are directed graphs, so they got nodes and arrows. It's directed, so the arrows point somewhere. If they were arrows on both ends, it can be called undirected. And then they have weights. Usually they're positive for a lot of applications, but they can be negative. And, this connects to this with a weight of 1. And you might interpret it different ways. You could say, like, how much does it cost me to get from 0 to 5? Well, it's 77. I can't go directly, but I can go here for 3. That's 80. Minus 1 is 79. Okay, so that might be my one possible path. I might go 77, 78, 79. Okay, same cost the other way. I might go minus 2, minus 1, minus 3, minus 2. Okay, so it turns out this is my shortest path of least cost, I guess. Although, because there's negatives, that's really kind of weird there. But, it could be distances on a map. It could be oil pipeline capacity, some value for that. Okay. And this page, they say they're giving you examples of things that can draw this stuff. Now, some people are just after draw the graph with the weights on it. I'd like to say the position from the weight here is 77 is so high. I'd like 0 to be in this corner and 3 to be practically over here, because it's like the farthest distance of any of these 2 points or 2 nodes. And so this graph is this one is focused on labeling a weighted graph. It's not focused on making the distances as realistic as possible. So another way to think of it is like a map of a country and getting city to city to city, kind of this traveling salesman problem sort of thing, minimize your cost of driving from place to place. And you may care, the physical distance may be the thing that gets you. But they mentioned GraphViz, which I've used before. Let's capture that. Mathematica does something. Haskell has the package. Another GraphViz fan. And GraphViz has a bunch of drawing tools. I saw, R. Graph thing. Never heard of it. But it just has a bunch of suggestions. Visual Studio has a draft drawer. Yeah, it doesn't sound like it's doing what I want, but okay. All right, so suggestions there. GraphViz, there's one called Neato, if I can find that. Search. Yeah, they call it spring models, which I think makes sense to me. You sort of treat the distance, you treat it as being like sticks and springs, and you may be able to compress it or stretch it, but it has sort of a natural length it wants to be. And so the distance between the points is determined by that natural distance. And then you try and adjust the graph in a way that kind of minimizes the difference between the minimizes the amount of stretching or compressing that's going on. Now I know I saw, well, let's try this. No. That's the problem with searching like stuff like this. You find a million things, and you can't remember where they all were. Okay, but neato is designed to do this spring model, and that's the kind of thing I'm talking about. Notice it handles about 100 nodes and all that. Okay, they mentioned a couple papers, and I've got those links. Let's see. Well, the test reflects. Sorry, I'm backing up. If it reflects the shifted up or shifted down, there's a bunch of tests for Parsons code to make sure they got the right direction going for things. If you're talking about the sliding horizontally, I'm not doing that yet. I'm just doing this linked one. I almost wanted to just like do 1 versus 0, but I don't think it'll distinguish enough to make the graph interesting. But it's a weird open problem. You know, I've got a lot of possible solutions and ideas going around, and I just had to pick one that looks, you know, easy to implement and get something for this. I haven't seen this done for music analysis like this, so I don't have to worry that, you know, I don't think I'm stepping into a field that's just totally, you know, covered and has standard solutions and stuff. So I can try kind of anything. Let's see, oh, here we go. Yeah, so these papers, graph drawing by stress majorization, I know I got a link for that. I think that's this one. And we'll look at that one for a minute. When I say research, man, it's like, oh, bring out your math hat and all that stuff. Okay, so what they're doing here is, I think they're basically doing the same idea of a spring model. This is the one used by neato, the GraphViz version. So it's taking this spring model and then trying to say, well, it's energy optimization. Like, how can you do this with the least stress on the whole system? And there's this notion of multidimensional scaling. Now, I learned about that. I was in information retrieval, you know, document stuff for a while. And this was one of the things that was relatively new, I don't know, 10, 15, 20 years ago. But we were definitely talking about it in the context of comparing documents. And so again, the idea is the pairwise comparisons, whether it's complete or not, sort of define these distances, and you can imagine a multi-dimensional space, you know, maybe one dimension per document even, you know, just complete multi-dimensional space and all the connections between them. And multidimensional scaling sort of says, let's break it down by, let's find out if there's kind of a transformation in a dimension that gives us the most information. And so it almost looks for the most spread. And so think of if you tried to list a bunch of documents in an order so that any two that were super similar ended up very close together in the list. Okay. Well, a one-dimensional scale, it's going to be kind of hard to do that, although that kind of is the Dewey Decimal System, right? But it's maybe inadequate to do that because, you know, this one is writing about, this one's writing about graphs, springs, multidimensional scaling. You know, it's kind of on a bunch of topics, and lots of things are on the intersection between things. Okay, graph drawing has its own subcategory of stuff. Stress majorization has its own category. We're putting them together. There may be a few people who do this, you know, in sort of ways, but it'd be hard to, you know, put it in one line. And so multidimensional says, well, take one dimension, and then with whatever's left, there's some amount of, kind of like in statistics, you can fit a linear line to something, and then you've got all these outliers, and you can fit a 2D curve to it, getting more of them, and a 3D curve getting more, and so on. And so multidimensional is kind of going the other way, and you cut down the number of scales to whatever level you want and try and account for things. But on each dimension, it tries to kind of spread the documents out in a way that they match closely together, but not the same as the next dimension over. And I don't know, I thought it had more potential for information retrieval than I saw used. So I kind of wish I had really dug even deeper into this. But what I know it's doing is, it's got things in multi-dimensions and it smashes it down, to smaller number of dimensions. And it's kind of an open thing of how many do you need for a given set of documents. But, if you could take 1 million documents and scale them 10 ways, and you could find a document, look at its neighbors in each dimension, and have a decent chance of finding something related. Kind of cool. All right, I'm going to go through some math here, and I don't think it's going to kill me, but my goodness, it's been a while since I worried about this level of stuff. All right, so graph, basic definition, you got vertices, end vertices, and you got a bunch of edges. Binary relation means you connect, one edge versus the other. Okay, it's hard to visualize. Yes, it is. So we want algorithms that do the job. All right, and then this one is this equation to try and measure the energy in the system. And let's see if I can make sense of it. I think it makes sense. All right, so we're going to sum up stuff. I less than j says if you put them in that big 2D matrix, we're only going to take one triangle, either the top corner or the bottom corner, and work from that because they're symmetric. So we don't need to put both sides in, just need half the piece. All right. So xi minus xj. So what we're doing is we're placing two nodes I and j, and we know their distance. In our case, we have this probability or pseudo probability similarity measure, that tells us how far apart they should be. Okay. And so that is there. It's almost like a statistics thing. We're taking the difference of things and squaring it and summing that up. That looks a lot like, variance or something to me. So xi is the place where we're placing node I. And I don't know, I'm not sure if that's considered a two-dimensional point or not. Okay, but I think this is xi minus xj. We're going to take the 2 points, and I think these double bars are not absolute value, but they're distance computations. So, the difference of the squares kind of thing. Okay, or square the difference. I'm not quite sure how we'll say it, but calculate the distance between 2 points, okay? And this is the distance between these 2 points drawn on the page versus the ideal distance, and then we square it, okay? So if that were negative, it would turn positive, and we add a little bit of a sort of cost, kind of a quadratic shape to it, so it's not a strict linear kind of thing. Okay, then we have this wij. We got to find out what that is. Okay. Wij is a normalization constant, okay, equals our distance to some negative power, all right? And people have chosen 2, and they've chosen 0, and they've chosen 1. You can see why you'd like 0, right? Because d to the 0 is always 1, so you can just ignore that term. Alpha equals 1, it's kind of the inverse, so you're kind of adjusting it. And I don't know, alpha 2, what we're doing, I guess we're minus 2 is that the square root of it? Minus a half, so the 1/2 is the square root. So it's the inverse squared of it. Okay, you can tell. All right. Suggesting dij to the linear network distance to convey the clustering structure. Yeah, I mean, that's, I think, what we're saying. All right, so in some sense, I mean, I think this defines the whole thing for us in this interpretation of it. um, okay, so we desire a layout to minimize this function. Okay, so that's our approximation of those target distances. All right, so we make a layout. We compare how far the layout nodes are versus how far we said they should be. Square that and adjust it so we get some sort of normalized value, and do that for every pair of points. Okay, so that it's definitely some decoding math wise, but I think it makes sense. I mean, some of you are probably like real math people, and this is just like me, but I think that actually does make sense to me. Okay, and so what we're going to do is say, what's the best way to set up these xi points, right? Like we don't have any information about them to start with, so we're going to have to take something and do it. Okay, now they mention this other paper. Okay, with alpha equals 0 is the stress function in multidimensional scaling. Okay, and 17. All right, Kamada and Kawai, they had a way of minimizing this function, and they're saying, well, in MDS we have a different way. So the function is sort of independent. Like I said, it almost reminds me of a variance or something. It's a very natural distance measure, I guess you'd say. So they've designed Newton-Raphson is like approximation, kind of iterative approximation. So if they try and minimize, it's local, so they try and minimize the point distances kind of between a point and its neighbor or something like that. And the point of this paper is, we have a different way to adjust it globally. And the nice thing is guaranteed monotonic decrease of energy value. Okay. This function, remember, we want to minimize it because it's how far off are the distances that you choose from the distances we said it should be. And so if you minimize that distance, then that's the energy value. And guaranteed monotonic decreasing says every step through our process, majorization, decreases that energy value, or it does not increase it, but it may decrease it. It never increases. It might stay the same, I guess. So their contribution is doing this in a graph layout. Okay, so that all makes sense to me. Now I'm going to keep going. Stress majorization as described in the MDS literature. Okay, so I heard about MDS. I didn't know this function, so it tells you where I am a little bit. All right, so stress is the function up there, distance between points minus that. Okay, they're going to take this minus alpha with alpha equals 2, so d to the ij. All right, and then they do their algebra on it. So break this formula up, okay, and you get these terms, wij dij squared for all those places, plus this x minus x2 squared minus twice of this delta ij. Okay, and then what's delta ij? Well, that's wij dij. Okay, so here's where I'm going to start getting lost. In a way, okay, the first term is constant independent of the layout. These numbers are all defined. They have nothing to do with x. The x's are the layout points. So you could pre-calculate that one. All right. Second one is a quadratic sum. Okay. Can be written using LW. Okay. TR and LW. Okay. So right there is where I'm lost. Okay. I've heard of Laplacian transform, but I don't know how to do it. Okay. So n by n weighted Laplacian has these entries, minus wij, or the sum of a bunch of omega, or I don't know, w or omega, ij, or the sum if the numbers are the same. Okay, some other sum. Okay, And then the third term is more involved, like, oh no. We'll make use of the Cauchy-Schwarz inequality, xy greater than or equal to x to the ty. Okay, I don't know what t is there. Okay, so right in here, page 2, I'm lost. I'll have to be digging into these Cauchy-Schwarz and Laplacian and this and that and the other. Okay. I kind of trust that it's okay. I mean, this is, the shape of it sounds okay to me, for what that's worth. Oh, xt is x transposed. Okay. So, the axes of layout are x1, xd. In d-dimensional is the layout by n by d matrix X. Okay. Axes x1 to xd. Okay. So I guess the whole thing is X is this matrix. We're doing I don't know what TR is, but X to the T is a transpose times this Laplacian number and times the original matrix. Now, I don't think they said what TR is. And I don't know. Okay. Unfortunately. All right. I'm hesitant to go further, but we'll just see what we got. Okay. Right. Okay. So for each axis, we have to solve this formula. Okay. Yeah, it's going to take some decoding. Known to be a positive semi-definite with a one-dimensional null space spanned by 1n. Okay. It has a global minimum, invariant under translation. That's good. Okay. So this transfer is invariant. Okay. We want to make the minimizer unique. We ought to take x1 equals 0. Okay, and n minus 1 by n matrix. Okay, and then I've heard these two mentioned before. They're different ways of tearing apart this thing. Okay, iterative optimization. Given a layout, compute a layout xt plus 1, so the stress is less. All right. So that says we're decreasing this stress formula, which is our goal is to minimize it. Yeah, so terminate when the difference between the two is less than some delta or epsilon. By 10 to the minus fourth. Okay. Summarize. It involves iteratively solving number 9. Okay. I don't know that I can do that. All right. Okay. Use Cholesky factorization or conjugate gradients. Okay. What I think they had somewhere a conclusion that many times CG is faster, and that's what they've used. Okay, I don't know. So this one, come out on Kawaii. So the idea is fix the position of all nodes except one node. So whatever graph you have, take one node and find a position on the graph that's better for it. Okay. And, yeah, so if you do that, you can lock one node, then move to the next one, try and get better, next one better, next one better. I can kind of visualize that working, and they're saying it's guaranteed to strictly decrease, and collection oscillations and non-convergent are impossible. So that is good news. I don't know if, yeah, okay. They've implemented the global one and haven't really done the local one, but, all right. So now I don't know if we have some pictures. Sometimes that's nice. How long does it take? Well, majorization seems to drop quicker. but start worse. Okay. Time in seconds. That's kind of helpless, useless. As the size of graphs increases, advantage swung to majorization. Okay, cool. Both reach the stress is not monotonic. Oh yeah, you can see that here. So it goes across, down, down, up, and then down. So we made the situation worse and instead of better. Okay. Whereas this one, like really by two seconds in, the last second and a half, you didn't really get any improvement. Interesting. Okay. Now, distribution to graphs, decay lower than random. Okay. So that may be good for it. And I think we'll find that's the case for us, that these distances are not random. They're from songs that are purportedly the same song. It may be that 2 or 3 songs had the same name and showed up differently because of that or something. All right. But here's some results of theirs. This one they like nicer because you can kind of pick out clusters more easily. There's one. This is a looser one. That's a loose one. Maybe a loose one. Maybe a tight one inside there. I don't know. But you can sort of convince yourself you see them. And I don't think it's terrible here either. Uniform edges. I'd have to go read their definition of what that means. But they know they have some highly connected points in the center and something ought to cluster there. I don't know. To me, these clusters look a little more clustery, but who knows? Some of them are probably not really there. Okay. Yeah. All right. More pictures. Okay. And this one definitely feels like more clusters. This one feels like it's just jumbling all in the middle. Okay. Yeah, they mentioned neato and GraphViz. Okay. I don't know what to do other than keep going on the research here, and then I think we'll do something, and anything may be sufficient to see stuff pop out. I hope so. Okay, so this is the research they built on Kamada and Kauai. Okay. Right. We're trying to get the geometric distance. So how far apart are they in a picture versus the graph theoretic distance should correspond. And they do that with this notion of a spring. Okay. So spring has a steady state. It needs more energy to stretch it, and it needs more energy to compress it. And sometimes those are not symmetrical. Often they're not, but that's okay. All right. Graph drawing problem. Okay, we could do lots of things. All right. A graph can be decomposed into connected components in number of vertices plus number of edges. Okay. They're trying to talk about, do you like drawing A or B better? They both reflect the same graph connectivity. Okay. Most people like A, even though it's got crisscrossing lines, where B goes out of its way to avoid it. Okay. Now this, okay, we'll go through their discussion a little bit. It's kind of similar. Okay, so P is particles in a plane corresponding to the vertices. Okay, so the P is the dots we're going to draw for each one. And again, we're taking a distance. Now their distance doesn't look, I don't know if that's, I'm not quite sure how that P1 minus PJ, if this is really absolute value of their difference minus the desired difference, Lij. Lij, original length of the spring. Okay. Distance between two vertices in a graph is the length of the shortest path. Okay, so I don't think we're going to worry about shortest path per se, but Okay, where L is the length of a single edge. Okay, so they're just scaling that there. Right, you can find it by looking at the furthest apart points. Okay. Okay, here we go. I think they're kind of going to the same thing the other guy did. Kij, we'll have to find that one, but you're taking the x points minus the, x, the square of the differences of the x's, the square of the differences of y's, the length of the desired distance squared minus twice of the sum of this stuff. So that sounds a lot like the other equation. Remember, they broke it into 3 parts. Okay, so they use Newton-Raphson. So you're trying to basically get the derivatives to go the right way. I mean, you're getting closer by figuring out, is the derivative closer in effect. Okay, got to solve 2 simultaneous nonlinear equations. Yay. They can't be solved with Newton-Raphson. Okay. All right, here we go. We adopt another way. We only move one particle to its stable point at a time, freezing the other particles. Okay. We view E as a function of only X and Y. We could contain a local minimum using 2D Raphson. Then we get a local minimum which satisfies 6. Okay. Choose the particle which has the largest value of delta M. And then these correspond to the equations. Okay. My confession is I was a math major, but I hated calculus. So forgive me if I'm blurring over these derivatives. I ended up doing a lot of statistics, which does need calculus, but I hated that part of it. All right. Okay, symmetry and not, I don't care. Interesting how these get drawn. You can almost see PostScript displaying them. Okay, so isomorphic graphs looking isomorphic, I guess. Okay, weighted graphs. Now these two, yeah, I think they have tried to approximate them a little bit. 2, 2, 3, right? That's not really right. 1, 1 squared of 2, 3 is not 2 times square root of 2. So even though this looks like almost a right angle, they've adjusted it somewhat. Okay. So 3, 3, 3. The 3s all look about the same length. The 2s look a little long to me. The 1s look short enough. But they've had to adjust things and account for things to make it work. Okay. You may not be able to draw a graph with all the distances you're saying. Okay. So, I mean, if you have 3 points with the same distance to each other, it makes a triangle, right? Equilateral triangle. If you have 5 points, like you can't put them all exactly that far apart in one 2D plane. Okay. Concluding remarks. Okay, good. Weights or geometric distances. Yes, that's what we've done. Okay. Right. Okay, what else we got? Let's take this one first. My alma mater, Virginia Tech. Okay. This one is talking about graphs generically. So a weighted graph is, like I mentioned, the distance, or think of a pipeline with, capacity 15 and 10 and 20 or whatever. Yeah, it could be lots of things. Okay. Cost in some sense. Okay. Now, the shortest path algorithm is kind of like, how do I get from one point to another, minimizing my overall cost of transport? Okay, so let's take C to H. Okay, there's no point going here, 25, 40, 45. Okay, if we did 40 and got here 60, it's not going to get smaller. 20, 30, 35. Okay, so it would actually be better to go CEBH rather than CABH. Okay, and that's the classic traveling salesman kind of thing. I want to minimize my cost of getting from A to B, or making a loop or whatever. And Dijkstra had an algorithm for this, and I'm not going to go through it. I don't remember it for one thing, but I think he builds up partial distances, and if it exceeds the distance of one that already got there, then there's no reason to try down some other path or something. Okay, got to have non-negative weights. There's another algorithm. And then we also have the notion of a minimal spanning tree. So this is a different take on how we're going to arrange things. And it might be an acceptable way. So this is Jarnik-Prim. Often heard it called Prim's algorithm, but I think Prim was later. Yeah. Okay. And so the spanning tree is a different concept. It's saying, I want to have each node in here, but I want to pay the least to include it. Okay, so it's cheaper to get node C by going B to E to C than it is by going B to A to C. Okay, and so we don't need this edge in the final graph, nor this one. Okay, cost of, well, I think this is probably A, B, C, D, E, F sort of thing. All right, but we can work out these costs and get this spanning tree. Basically, you could kind of look at something as the root of it, and then the nodes 1 away are children, and then 2 away is grandchildren, and so on. Okay, a different way to look at it. Now, I did some work with a genetic company for a number of years, and I'm trying to remember. They had, is it called clades? I haven't looked this one up lately. There's a way of, you organize these things based on what you assume their evolution is. Okay, this is a good picture. Right. So these two are very close, so they share a common parent. These two are sort of further away. We can get, I guess if I take this one, this one and this one are somewhat related, but indirectly related. Okay. There's a lot of distance from here to here. But this, last common ancestor. So think of evolution. The time in the past is here. This was, one-celled amoebas or whatever. They split up. Maybe it's, we'd like to say vertebrates and invertebrates, but it's probably the other way around. But, let's take vertebrates here. And maybe this is the fish family. And over here, the reptiles have broken out. So within this, these are closer to each other than they are to these or these. All right. And so now the question is, where do you get this organization? And the way I know of to do it, let's see, they have an example. No. You can find characteristics that are common across them. Okay. So I don't know if I can do it with these. Okay. There's some things that have tails and some things that don't. Okay. And what we have here is all these things have tails and then humans don't. So there's sort of a split off there. Gorillas and chimpanzees have more characteristics in common than gibbons and chimpanzees, say. Okay. But you can define these characteristics. Now you can't, you usually can't definitively say that one evolved from the other or didn't, because sometimes things go away and then re-evolve in the same line and stuff like that. But there is a way to do this. It's not numeric. It's more attributes and present or absent. And if you have the most attributes the same, you're very similar. And if you're different, then you're more different. Now, I believe I ran across Khan Academy clade. Let's try that. Maybe, was it this? Yeah. Okay. So this is another way we could go if we can define I don't know. Can we define attributes on these songs? I guess that would be a different approach, right? We could do something that says, number of things going up versus number of things going down. Are you mostly up or mostly down or mostly across? That would be interesting. I don't know. Characteristics, are you similar rhythm, similar time signatures, similar whatever? I don't know. But there definitely is this notion of how you can do these. These are probably checked because I was on these pages at some point. Okay, let's try this one. Yeah, building them. Okay, transcript. Yeah, I'm big on those. No. Okay. I don't know. We'll skim through.
The word Genesis.
Okay. Yeah, this is what I recall. So you can find characteristics, and then the ones that the characteristics that cut across, you sort of use that as a division. Okay, so it looks to me like Jaws is lungs is another good one. All right, so we might choose to do it by lungs or Jaws. And then we'll choose to differentiate that and use that as a dividing line. These animals have lungs, these don't. Okay, so sea basses and lampreys, we know that's the fish family versus the reptiles. Reptiles, birds, and mammals all have lungs. Okay, so that would be a natural split there, is lungs versus not, and put the fish in the lungs. Now Jaws versus not, it sort of cuts across. Some fish have it, some don't. We could have decided to break apart on Jaws first for whatever reason. But given all these, we can produce the kind of tree we've got here. And again, that tells me A and B are closely related, C and D related to each other and somewhat related to A and B. That sort of clustering would be helpful for us. I mean, I think anything for us would be useful. I just don't have characteristics. I don't think that I can use distance. I don't think distance is going to quite do it. Notice this gets away from the 2D layout that we were talking about too. And that's okay. If it works, I'll take it. Can we adapt a distance thing to this? Well, okay. Another one. Let's see. Agglomerative hierarchical clustering. That's it. Okay. I think I had this page up yesterday. Hierarchical. Okay. And let's see if there's a picture we can use. Well, I don't think it's going into the details of the algorithm enough to make sense. But the idea is you find two that are close. And I don't know, I've seen a graphical drawing thing that did something like this, but you find two that are close to each other, and then you sort of make imagine a center to their cluster. So maybe you have BC next to each other, and the cluster is kind of right there. The BC cluster surrounds them. And then you say DE are pretty close. Well, put them in a cluster. Now, what's closer? Well, is BC closer to DE? No, turns out F is closer, so let's make a DEF and draw these together. And then BC, DEF are all relatively closer than A. Okay, so we might be able to do something like that. Okay, optionally, one can compute a distance matrix. Okay, as clustering progresses, rows and columns are merged. Yeah, it's a common way to implement it. The single linkage clustering page. Okay, let's take a look there. I don't think I went there. Agglomerative it's the word glue is in there. Effectively, they sort of stick together. Okay, so yeah, start with each element in a cluster of its own. Then you figure out ways to combine clusters into bigger clusters until everything's in the same cluster. All right, each step, two clusters are separated by the shortest distance are combined. Okay, the linkage function is what differentiates them. Okay, well, this sounds like a doable kind of thing. Naive algorithm, that sounds like me. Okay, basically erase rows and columns and merge them into new ones. Start with n by n with all distances. That sounds like us. All right. Clustering is assigned as numbers and levels. A cluster with sequence m is denoted m. And proximity is denoted by distance, d/s. Okay. Oh, excuse me. Well, I don't know. This sounds kind of doable. So the real thing is I'm gonna take the question's like, how do I merge things together, right? Now I can't, this is not working on space. The result's going to look more like that tree, the phylogenetic tree we had in the con thing, more like one of these two cluster, and so on. But that's okay. I don't know what makes it single linkage. Okay. Group clusters bottom up. Combine two clusters, the closest pair not belonging to the same cluster as each other. All right. Produces long, thin clusters with small distances. And opposite ends have much further. So this could lead to difficulties. Okay. Pop in astronomy. The friend of friends algorithm. Okay, well, that sounds nice, friendly. All right, here's neighbor. Oh, the resulting cluster can be a dendrogram. Okay, that's exactly what this is. Okay. Cladogram is just because the clades or clads or whatever are very similar. I don't know the difference between it. Maybe they're both considered. Yeah. I guess because it's an evolution thing with ancestors, maybe it's kind of regarded separately. But dendrogram is the right thing to talk about from my point of view. Okay, clusters by analysis. Yeah, this sort of hierarchical thing would be fine for me. I mean, we can figure out whether it should be horizontal or vertical or whatever, but that would be all right. And notice here's three different ways to draw it, right? This one's kind of linear to linear to linear working left, and this one goes these sort of upside down U's hierarchically, and this one's kind of a diagonal branching thing, and I don't even know how to interpret this one. Yeah, don't know. They're using two different dimensions to do two different dendrograms. Okay. Well, I can imagine drawing dendrograms. I mean, these brackety things look drawable. These look drawable too, for that matter. I mean, I'm imagining, I got 39 versions of Deck the Halls. Somewhere have, I think it's 198 versions of Barbara Allen. I don't think anybody's going to have 500 versions, but maybe we can work something out. And I could imagine that you don't need to see the individual ones, so you just get the clusters of them. Might be very useful. And yeah, okay. This has possibilities. All right, so where's that single? I lost my single linkage clustering. Open a new window. All right. Well, I think we can do this. Because I think what you do is, in effect, we're going to merge a cluster with another cluster where initially it's individual elements. And I think we could say, like, the average distance, the distance to another cluster, well, I don't know. I haven't heard centroids mentioned, but the idea is you could put a dot in the middle of each one. And I think if you said the distance from this cluster of node 1, node 2 to whatever else is out there, well, it's either clusters or individual things, we can sort of average the distance to the contents of it, is what I would say. And come up with some sort of measure like that. Okay. All right. Well, my mind's a little fried from all the math. If anybody's left out there, let's take a. Oh, hey, let's see. I don't know when you joined. I've been staring at the other screen too long. I'll give you the quick talk through of this. We have a bunch of different versions of a song. Nos Galan is Deck the Halls. Da, 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 da. And we've done a Parsons code graph, which tells kind of the direction of each note. Is it higher or lower than the one before it or after it? And if you do that, you can see that these two versions are starting out very much the same. Okay. And this one kind of looks like a chunk in the middle. It might be more or less the same. And then you get down here and this one's mostly going down. This one's going across, wandering down, down. We can see that some of these things belong together and some of them don't. And I'd like to make some sort of 2D representation that shows me which ones are close and which ones are further away. And the ones that are close, like that look sort of like this one, to some extent, I want to listen to those and say, are they really the same song, just kind of altered slightly? And, this one is probably not going to be the same song. It's just totally, totally different motion. So we're looking for ways to do that mathematically. And we've gone through a bunch of painful math papers. One set was basically, the distance between how close are any two things, treat those like springs, and then connect all the springs together and try and minimize the amount of stretching and compression of those springs. And that's a reasonable sounding way to do it. Another way we looked at was, I'm blanking out on one of those, but we looked at another algorithm that was sort of like a shortest path kind of thing. Didn't really think that would help. Then we started looking at these trees. And so I think, A and B are close to each other. They're closer to C and D than either of those is to E. This kind of breaks out things, and you get diagrams like this, showing the little clusters, working your way from individual things over to the whole thing, and different ways of drawing that. Okay. So I think what I've settled on is this, what they call single linkage agglomerative clustering. Single link is saying it's working between pairs of elements, I think, or pairs of clusters, not trying to do everything versus everything. And agglomerative means we start with individual, everything is its own cluster, and then we kind of glue together the ones that are more and more similar until we got everything in the pile in one big cluster. And we got a little bit of math. Here's a distance function that we're describing between them, and then we can do we run through this algorithm that takes them all into account and builds up a matrix that represents them. Okay, and we haven't gone through the details of this yet, but we will. And I think that's what I'll try and implement first. And given this structure, if I can draw this dendrogram for my songs, and this height is meaningful here. Interesting. Okay, then we'll have something. Okay. And yeah, so, this is nice. So here's this algorithm. What does it get? A complete linkage is probably N versus N. I don't know what these other ones are, but I've seen their initials. But you can get different things from the same input. Okay. This one comes out A, B, C, E, D. This one comes out A, B, E, C, D. And all three do. So depending on the algorithm, it'll change what you get. But I think given what I'm working with, if I find these ones that are pretty close to each other and ones that are far away, and there's a little iffiness in the middle, I think that's natural and I can live with it. Okay. How fast are these things? Well, naive algorithm is O n cubed. All right. We can get down to n squared with S-link algorithm. All right. I'm looking at 100 maybe items, 200 items. So 100 cubed is 10,000 times 100 is that a million? A million entries is a lot, but it's probably doable. N squared would be nicer. Oh, both those are optional. So S-link is a good algorithm, but we're not doing that one for starters. I'll do the naive one and see how it looks. It may be a total mess. Okay. Another one based on the equivalence of naive and Kruskal's minimum spanning trees. Okay. We're using Prin's algorithm. We did look at that one. Without binary heaps takes time O(n) squared and space O(n). Then apply Kruskal's algorithm to the graph to get clustering with n log n. Okay, so also possible. All right, but I think we're due for a break, so definitely. We'll take 3 or 4 minutes. For me, that's going to be coming back at 2:30, but half past the hour in most places, not all, because we're talking time zones here. All right, so let's take a break, and I'll see you in a few minutes, and we'll start in heading towards a version of this algorithm. Oops, I've left this off all day. Okay, and break. All right, welcome back. Okay, yeah, it's a mess. Let's see. So I think I've settled on this. So let's capture this. Our to do. Let's see. This is background research, and then our approach is this and dendrograms. Okay. It definitely wasn't how I was planning to do this, but we'll take a go. Excuse me. Let's put that down here. I think we've done enough of that. All right. So correlation of all songs to all songs, figuring out a clustering. That's kind of what we're doing. So I think we're going to go through this algorithm a little more detailed and identify pieces it needs. And I think the dendrogram will come much later. But, well, let's move these up. Let's say study this. Okay. So study, well. Okay, so we start off, each element is in a cluster of its own, and then we combine them into larger clusters. At each step, the two clusters separated by the shortest distance are combined. So there's a linkage function, so we'll need a linkage function. In single linkage, it's termed by a pair of elements, the closest to in each cluster. Okay, nice. Okay, nearest neighbor. So I'm just going to pull some terms in. A linkage function. Let's see if we can say what that does. Determine distance between two clusters. Okay. And the distance is determined by a okay. Let's capture this sentence fragment. Determine distance between two clusters, and we're going to do determined by a single pair of elements, two elements, one in each cluster closest to each other. Okay, so all right, so we know the individual distances. Okay. Nearest, we're going to do nearest neighbor clustering. Oops. And that is okay, that's this. I'm not very good at copying. I don't think something gets in the way of my selection. Oh, is that the right sentence? Yes, it is. Maybe I just can't read. Okay. Right. Linkage function. Can I select this? Yeah. We'll see what that draws in here. Who knows? Yeah. Okay. We'll get a little LaTeX, I think. Okay. Agglomerative. That's kind of an interesting word. Okay. So we need a proximity matrix. Yeah, welcome back. And it's going to do this. Okay, so it contains all the initial distances. Clusters are assigned numbers. Okay, and levels. What are levels? Okay, clusters have levels. And they have, I don't know what we're calling our nodes. Elements. Okay. So a cluster well, let's see. Cluster has a sequence number. It can compute distance, proximity. Clusters are assigned sequence numbers. Okay. So it's got a sequence number, a level, and a set of elements, which could be clusters. Cluster contains a sequence number, level, and I don't know, contents, children. Okay, so I'm hearing composite pattern right there. You know, it's recursive. And we have a leaf, which is a single element. Okay. Proximity matrix contains all distances. Okay. Begin with a disjoint clustering L0 equals 0 and sequence number M equals 0. Okay. All right. So, yeah. Well, we definitely have the notion of clusters. That we can bring out. It's either children or big things. And we've got distance stuff that we can work out. This proximity matrix, I guess that comes before the algorithm. I'm almost in the opposite order. Okay. This is unusual for me. We're TDDing within the context of a predefined algorithm, or at least a somewhat defined algorithm. And this thing, okay, it keeps going until everything's in one cluster. It's got a lot of work per step. Okay. And we got these distance functions. We're going to have to keep them straight. The distance between clusters, the distance between items. Okay. Begin with the disjoint clustering. Level 0 equals 0. Sequence number m equals 0. Find the most similar pairs of clusters. Okay. All right. So I think given the structure we have, I'm going to try and test drive clusters, linkage functions, proximity matrix, and then this neighboring algorithm that we're going to try and follow, kind of in that order. It's not, usually I try and drive top down, or from a skinny but whole story. This time I'm just kind of implementing an algorithm and using TDD to put some rails on it as I go. I'm not going to try and make a clustering that works for just two. Maybe I will at this point. I might do something on that order, but mostly I'm going to be putting together stuff. I imagine this is going to take at least a session or two. Okay. We got 45 minutes still today, but cluster's not hard to define, but the linkage function's a little work. This is a bit more work. This is going to be some work. This is not likely to be a one session thing. Okay. So I'm just going to dive in with what I can see being there, define something that looks reasonable, and go from there. All right. Well, cluster tests, I think what I've established to myself is none of these are actually cluster tests. They're all Parsons code tests. So let's move them over there. I'm pretty sure we already have a test class for that. Parsons code tests. Okay, so already comparing lots of things. Okay, similarity is something we're defining here. All right. And go back here. Now cluster tests. Well, let's read our to-do again. Okay, sequence number, level, and children. Sequence number is just distinguishing them. I don't know what we do with it. Sequence number M is denoted M. And it's naming the cluster, I guess. We increment that number. Set the level of this clustering to L of M. Okay. Well, we'll start with a number. It looks like just an integer. It gets incremented and not, I guess, referenced in this sense. Okay. Okay. Sequence number, level. Level looked. What is level? L0 equals 0. LM equals distance. So it's going to be a double for our case. All right. Sequence number, level, and children can be clusters or elements. Okay. So, what do we got? Test. How about cluster knows its elements? Just to get started. Whoops. Cluster C equals, well, I'm going to assume it's an enum type, a sum type. Cluster.element. I don't know what our element is. Well, in our case, it's a tune, but I think maybe we got to be generic over this. Let's just do integers for now. Integer 1. And if I ask, let's assert equal c dot elements, it should be the set 1. We'll see. Okay, can't find C, can't find cluster, can't find element. All right, I think I created the file for it. Well, do it the fast way. I did not. I guess I created a folder for it. Let's make a new file. Actually, I'm going to do this kind of inline for now. All right, so it's public enum cluster, and we're saying it's got a case element which takes an int. No, which takes something. Well, I'm going to say this thing is generic. E. Takes an E. And we need a variable elements is a set of E. And must be hashable, huh? Do I need a set? I guess I do. Right. Okay, and let's return. Can I do this? Just to get compiling? Oh, how about we write Swift instead of whatever that was? Okay. I guess we can use a let. Okay, the test can run. Should fail. Good. All right. Well, I'm gonna go ahead and put a switch self and do case element of let element. Let. Is this the best way to do it? I don't know if I can use the word element here. Let's return, yeah, return set. Just expand this. Okay, should fail the same way. Right, I'm ignoring it. Okay. Now, I don't remember sets constructors. Immutable Cocoa set, minimum capacity. Oh, there's a way to create sets. I thought it had a constructor that would take collections or sequences or something. Oh, it takes an array. There we go. Yeah, it works with a set of sequence of items. Okay, well, it's easy for us. Return element. Create cluster knowing only about elements. Oh, we also moved cluster tests contents to Parsons code tests and created the element. Okay. It's so easy. Swift really does make these recursive tree kind of things so easy with these enums. Okay, well, we kind of did this study. Let's claim it. For now, we'll be going back to it, I'm sure. That's not the right one. Okay, I'll just mention it down here. Need that link again, I'm sure. Okay, sequence number, level, and children. Well, we decided level was a real number because it's distances. Okay. All right. And nope. Cluster tests. All right, we still have cluster in here. All right. Well, let's make test. This was element cluster. And this is I'm going to use their vocabulary if I can. I mean, I think these are clusters, right? Huh. Yeah, I guess it's a cluster. Okay, and it's going to be kind of starting like this. Let's let C1 is that cluster. We'll make another one, C2. And then let C3 equal cluster.cluster with number, sequence number. What's the name of that? Sequence number, level, and children. Okay, something's not quite right here. Besides the fact that it doesn't exist yet. Oh, whoops, just one, two. Okay, I think. The problem. Well, let's define it, and then we can work our way around it. Okay, so cluster is a case, and it's got. Let's do some aliases. Type alias sequence number equals int. Let's make that public. Okay, we define these, now I'm going to make sure I use them. Okay, so cluster is a sequence number, a level, and a set of cluster. Does that sound right? Okay, we don't need them in any particular order. I guess our clusters has to be hashable as well. Okay. Now we need the switch. Case cluster. Ignore sequence number, ignore level, and let's do children. Let children. And we're going to return nothing for now, just to get syntax okay. Now, you didn't pass. What's going on? Oh, I think maybe because I named it the same as that. Right, because it doesn't know it's children, as a matter of fact. Okay. Return. Okay, children is a set of clusters, so we have to, we'll have to ask the children for their things. So I think we want to do, okay, I think we want to do children dot, well, basically a reduce. We're trying to build the list of, or the set of all children. So we're going to take that, and then that's our starting one. And then I always get this order wrong. Oh, how many times can I do that? Let me just try children dot reduce. All right. Next partial result is a result and a cluster of hashable. I call it so far. Item in. Whoops. I'm not sure what term it objected to. Okay. Children so far, item in. All right. So given the set we've computed so far, and the next item, the result is take what you have so far dot append. Well, item is well, it's not right error. It's going to be a whatever one child is, which is a cluster. And we can take elements off that cluster. So item dot elements. Okay, has no member append. Really? I thought I just got it. So far. Well, that should be a set. Let's do this. Be explicit. Okay. Does that help? No. Value set of E has no member append. Okay. Do we have Swift set documentation here? Is it? Oh, insert element. Combining sets. I guess I could deal with this one. Form union. Insert the elements into the given set. Okay. Cannot convert value of type. Oh. I don't know that I want a new. Okay, we can do this. Okay, so let's see, that's inserts the elements into a set. It's not a sequence. Oh, so far it's a let. Okay, well, just so far dot union. It should be relatively cheap to form these sets. Okay, I think I'm there. Prefer reduce into over reduce that for copy on write types. Well, let's see what reduce into. Combining into, oh, I guess I could do that, yeah. Into result, I guess that gets me a var, yeah. Okay. Into this, now we could do form union. Okay, good to know. All right, let's check that in. Okay, so make cluster handle recursive case of having contained clusters. Yeah, well, the warning actually isn't coming from Xcode. I've got SwiftLint running, and you can choose if you don't want to keep certain rules, but yeah, it made the suggestion, and then I had to go look it up as usual. But it's been okay. I mean, it complains a lot about some stuff, but I think also I've been a sloppy kind of, I don't work with another group that can kind of give me like, oh, this is the way we do things, So I've just kind of had a pretty sloppy style, and it's made me clean up and make, like, I was very inconsistent about putting a space or not in between before colons and stuff, and just lots of little syntactic, almost character level things that I could make inconsistent enough, and it was good to catch them. And things like that, I mean, I tried to write it with the form union in the first place, but I wasn't passing in something modifiable so that it led me in the right direction. But yeah, I didn't get to use app code really, but I've used IntelliJ for Java and Kotlin for a fair bit of years, and stuff like that, it definitely would be all over. They really have built in a lot of good stuff there. But yeah, I'll muddle through this way. All right. So I think the thing I'm missing, and I've hit this with these recursive types before. I really have, I think my elements, they may also need sequence numbers. I'm going to go back to our description again, but I think, I mean, somewhere it said we were going to start with each cluster being each item being a cluster by itself. Okay. Disjoint clustering, L0 equals 0, sequence number M equals 0. So I think that's saying the next cluster. But when I combine things, I'm trying to treat them as clusters. Now the minimum distance is fine. Maybe they don't need an L. Maybe they don't need it. But at least sometimes I've had this thing where I have a common field I wish I could put above all these. I want everybody to have, maybe I wanted everybody to have sequence number and level. And if I did that, I would have to put the whole thing in a struct or something like that, and then break out the children as a separate thing. I mean, can I do recursive structs? Maybe that would be better. I always think of these as being independent things. Well, I guess that, yeah, I don't know. Let me search that too. Swift recursive struct. I've used the enums for this, I don't know, a dozen times now. Structs can't have recursive values. Okay, good enough. It looks like maybe the algorithm doesn't care about sequence number. Maybe that's not right. Find two clusters, insert them, merge them to a single clustering to form the next cluster M. Set the level to the distance. Update the priority matrix. Rows and columns corresponding. Well, how weird. I never really use those sequence numbers for anything. I just increment them. I love the example. Let's just take 5 random bacteria. Okay. Lactobacillus, we can make yogurt, right? Okay, we have 5 elements with the distances, pairwise. Okay. No connected. Well, that's not helping me, really. Okay. Well, assuming we have 2 elements, right, we're going to have at least one cluster. Okay, we may come back later and wish I had put this in a struct and with an enum inside it or something. What that would look like, let me just sketch it real quick. Struct X cluster. Well, I have to be hashable and E and all that stuff. All right, but I would define these 2 fields. Public var sequence number level. And then I would have to use cluster public cluster. Maybe I wouldn't need it. Let's say children of a set of element. I think there's something to recommend that. All right, so we're going to see if we can swap it in. What would that take? Would that work? Maybe that's the question I should have first. Do I need to reconstruct? Well, I bet I do, right? Because this cluster here, U, is the cluster of A and B. And if I throw everything in one thing, V would just be a set A, B, C, E, and I wouldn't be able to recover U from it. Okay, so I'm gonna leave this out, but something on this line, I mean, the children could be, well, what would they be? Can I do set of X cluster? That'd be recursive, right? Or would it? Cluster of element does not conform. Oh. Okay, it might have worked, but I'm going to keep this way for now. Okay. Is that enough to do anything with our algorithm? Okay, so what else do we need? Okay, we start with L0 equals 0, sequence number that. Find the most similar pair of clusters. So I need to be able to ask a cluster. I need to be able to ask a cluster, what's your distance to some other cluster? But that's all according to that proximity matrix. I'm still a little puzzled what the sequence number does for you. Okay, but I'll let that go. All right. It seems reasonable to ask a cluster, well, given a proximity matrix, I need to ask, according to this proximity matrix, what cluster is most similar to me? I don't know if that's an algorithm on cluster or not, but let's try and define the proximity matrix. Okay. It erases rows and columns, so it's going to have to be told get rid of certain rows and columns. That's fine. Okay. The proximity connect to all DIJs. Okay. The proximity between two clusters is noted is this, right? DXY, we have to look up. Oh, we have two matrices going on, don't we? Update the proximity matrix by deleting rows and columns corresponding to those and add one to the newly formed cluster. An old cluster K is defined by that. I think that's not different than this. Okay. Well, let's try this proximity matrix. So I guess what I'm wondering is if all my individual items, I mean, they said they would be stuck. Where is it? Single linkage clustering. No. In the beginning of agglomerative clustering, each element is a cluster of its own. So that says to me I've got to create a proximity matrix that takes clusters and defines that distance. Okay. Yeah. Let's define proximity. Well, let's pull this out first. This should be in its own file. And I said I had cluster here somewhere. New file. And I've been getting rid of this stuff where I can. Okay. Cluster. All right. And that should all build. Come on, Xcode, get with it. Okay, what's going on? Did I not mark the file as the right kind of file? Yep, I did not. Okay. I don't know, sometimes it marks them both, sometimes it doesn't. Refactor, extract cluster to its own file. Okay, let's start this proximity matrix then. Where's the test? I'm going to make cluster its own folder here. Cluster. Do groups have this problem? Share test. Clean. Okay. Righty. And now in here, we should add a new test for proximity matrix. Okay, and proximity matrix basically has to be able to tell distance between any clusters. I think I'm still going to need this definition of these, but okay. Well, in our case, distances are doubles. So we got to implement this rule somewhere. Okay, so distance between clusters. Okay, given two clusters. calculate the distance. So I guess we're defining this thing. Okay, and that always references little d. Okay, so d is a separate matrix. I'm going to have to keep that straight. All right. Okay, so where... And the other thing we have to do is remove and add rows and columns. Okay, so let's make our to-do. We've got at least a start on this one. Okay, I guess we're gonna... Well, let's make this function first. This distance function, given, I guess, given a priority matrix and another cluster, then give me a distance. So it's not a function on the priority matrix per se. Okay, we got to be able to add and remove rows and columns. What's a good starter test? Well, we can test it starts empty, I guess. Does anybody care if it's empty? I don't think they do. Maybe it doesn't. Well, how about assert false? I'm going to call it matrix, not P. Matrix contains cluster dot element 3. Okay. Well, yeah, I don't think you're right. In the end, it can't be, but I don't know if we're going to create it with an element. See, this is starting to make me think. I mean, this is not. This should only contain clusters, not individual elements, because we really want to ask. I think we really want to ask it for, like it was calling it, sequence numbers, right? We want to say for sequence number 1 and 5, what's your distance? Okay, I don't know. You're definitely identifying a real constraint there, that it doesn't make sense to have a matrix of no elements. Sometimes it may be worth it just to kind of make the edge case fall out. But let me add a note just as we do it. Okay, let's put this above this. Can priority matrix proximity matrix, I'm calling it priority, be empty. Okay, I'll just leave that as a point of order. Okay. Proximity matrix. Okay, and let's do this again locally just to get it going. Matrix. Okay, we got an instance, and we'll give it a function. And we'll just hardcode true just so we get a failing test here. Cancel. Here's where I pay for my genericity. E. Hashable. I don't know. I think I like it spelled out better. Okay. Now this is wrong. I don't even know if I want element. I mean, it's really, I think I'm really supposed to be asking about sequence numbers. Cluster of sequence number. And that can just be an int. Okay. Will the distance be infinity? Yeah. I mean, that might be reasonable. I mean, if you asked, yeah, I mean, if you asked for an element that's not there and it just says infinite distance. Do we have? We do have that. I don't know. Would infinity make sense? I don't know if it comes out very well, but the way I've got things defined for similarity now, I think it's almost backwards. Parsons code, it's giving us a number 0 to 1, which is it's not exactly a probability, but it's sort of a 1 is the most similar and 0 is the least. But over and over, it seems like we really wish that was flipped around. But to your point here, I mean, I think the no similarity is 0 in our arithmetic right now for Parsons code similarity numbers. They're really not. Yeah, they're really not distances exactly. Other than they're just scaled numbers 0 to 1. but to your point, I think contains is not the right. I think I need to ask it the distance from 3 to 1. If they don't exist in there, should be conceivably be 0. But that means distance is not correct. Okay. I think okay, convert int to expected type string. Oh, well, I didn't do distance, did I? Can I say from? I can't remember if I can use that here. And it returns, right now let's just double. This is crying out for more abstraction, isn't it? Okay, let's see if we got a failing test at least. Okay, we do. Let me keep track of this issue too. Similarity, can we use distance instead of similarity from Parsons code? I think you're, thank you for speaking up, because I think you've definitely convinced me that I should be using distance instead and make it work on that. The fact that it's 0 to 1 or whatever range it is probably not terribly relevant. But this thing of similarity being backwards from us is going to mess us up all over the place. The only reason we wrote similarity is because we thought we'd need it. All right, we have a failing test. It's 3:30 here, so time's up for today. I'll be back tomorrow at 2 to 4:30 p.m. Eastern Time or 6 to 8:30 p.m. UTC. Thank you all for speaking up today. I really appreciate the interaction and the suggestions. It really helps. All right, well, take care. Hope I see you tomorrow or some other time. Bye-bye.